This video and in the next video we will consider the elliptic function fields, and as we defined the rational function fields, we will define the elliptic function field in terms of its genus. The function field F is called elliptic if it has genus 1 and if it contains degree 1 divisor. So, to see the existence of a degree 1 divisor, it's not be the case always. For instance, when we consider the real numbers as a full constant field, but as I have mentioned before, if K is algebraically closed, in this case, it's easy to see all places are rational. But for the moment, as a fact, we just suppose that for the finite field, this is also the case. So that means when the constant field K is algebraically closed, or if it's a finite field, then we always suppose that there exists a degree 1 divisor in its divisor group. And again, like in the rational function field, first we see an existence of a rational place in the elliptic function field. Or let me write it briefly. Our claim is that there's a rational place. And in order to see that, by the definition of the elliptic function field, we know the existence of this degree 1 place, so we may choose, degree 1 divisor, and we may consider it. And again, we can observe that by Riemann's theorem, its degree is bigger than or equal to 2g minus 1, indeed is equal, so its dimension is equal to its degree plus 1 minus g. This is 1. So this is a non-trivial vector space, and then we know the existence of a positive divisor, which is equivalent to A, and since they are equivalent, they have the same degree. So since it is positive and it has degree 1, this shows us A prime is a rational place. So that means A prime is equal to P for some F with degree 1. And this shows us the existence of a rational place in the elliptic function field. Indeed, here let me change the notation for this, for fix this rational place. In the elliptic curve case, let me use with curl law, and indeed, maybe it's better to write like this. Let me fix the notation. We fix degree 1 place, and we denote it by O. And in general, if you check the literature of the elliptic curve, this degree 1 place is counted as what is called the base point, or the place at infinity, or the point at infinity. And by following this notation, we can observe that its corresponding Riemann-Roch spaces gives us the information about proper inclusion or the equality between the Riemann-Roch spaces. And indeed, again, if you consider the Weierstrass gap theorem, we know that this is isomorphic to K, and by using the Riemann-Roch theorem, its degree is 1 bigger than or equal to 2G minus 1. So its dimension indeed 1. So that means the Riemann-Roch space of this rational place is also isomorphic to K, and indeed we have equality, and this also gives us the gap. However, if you consider the other Riemann-Roch spaces in this chain, again, let me write Riemann-Roch spaces, and by Riemann's theorem, we can check the dimensions, and indeed we see that the other Riemann-Roch spaces has proper inclusion. Now, this inclusion, this proper inclusion, and this gap, I mean, in the rational function fields, we had the proper inclusion in the first, the members of the chain, and in general, we consider the transcendental, which lies in L of O, or particularly, it has pole divisor O, and then we see that we can write the F as K of X. And to be able to derive, indeed, we have extension of some rational function fields, and to be able to derive the equation of the elliptic function fields or the elliptic curves, what we do is to consider some transcendentals which lies in this proper inclusion, and to write their algebraic relations. So in other words, first let me choose a transcendental which is an element of the Riemann-Roch space of 2O, but not in L of O. Indeed, from also discussion sessions, we know that its pole divisor is 2O. And similarly, let me choose another transcendental Y1, whose pole divisor is 3O. And indeed, this shows us, if we consider the elliptic function field F, and if you consider its extension over the rational function fields K of X1 and K of Y1, by using the degrees of the pole divisors of these functions, we can see that indeed F has extension degree 2 and 3 over K of X1 and K of Y1 respectively. And indeed, because of this relatively primeness, indeed we can also see that our elliptic function field is nothing but K of X1 and Y1. And if we are able to write the algebraic relation of this transcendental, we will be able to derive the equation of the function fields, elliptic function fields. And for this purpose, let me consider some functions which are in some sense generated by the transcendental X1 and Y1. And we can easily observe that they are all in the Riemann-Roch space of 6O, the divisor of 6O. And we have 7 elements. And the dimension of this Riemann-Roch space is 6. They are supposed to be linearly dependent. So indeed, This allows us to consider some non-zero constants denoted by alpha 1, beta 1, gamma 1, delta 1, epsilon 1, lambda 1, and mu 1. Not all zero, such that this gives us the non-trivial linear combinations of these functions. So here, first let me observe that indeed alpha 1 should be non-zero, because otherwise y1 will be root of degree 1 polynomial degree 1 polynomial over k of x1. You can easily see that if you replace it y1 by any indeterminate t, we can see that its minimal polynomial is degree 1. And in this case, extension degree is 1, but this gives us contradiction because of the degree of the pole divisors of x1. Yes, we know this extension degree is 2, and this is not possible. This is not possible, and this forced to the coefficient alpha 1 should be non-zero. And similarly, the coefficient of the x1 cube should be also non-zero, because again, otherwise x1 is a root of degree 2 polynomial over k of y1, and this gives us the extension degree as 2, but this gives us contradiction because we know that this extension degree is the degree of the pole divisor of y1. So now we multiply this equation by a spatial constant which is produced by this non-zero alpha 1 and delta 1. And by considering these linear transformations, we can reduce this equation into this one. And indeed, we can also see this since these products are constant, pole divisors of x2 and y2 will be the same of the pole divisors of the transcendentals x1 and y1. And indeed, we can write our elliptic function field with respect to these transcendentals. And from now on, to be able to reduce the Weierstrass form, what's called the Weierstrass form, we suppose that characteristic of the base field is different from 2, and by this assumption, again, we specially consider some transformations which allows us to write the same equation in terms of this x and y. And similarly, we can also observe that the pole divisor of y is equal to the pole divisor of y2. And of course, I think you may also need to check the pole divisor, so I will consider it in the discussion session. Again, similarly, we need to verify that the pole divisor of x and y will be the pole divisor of x2, y2, or x1 and y1, so that we can write our elliptic function field in terms of two transcendentals, which can be written with respect to this algebraic relation. Or in other words, it can be written as y square equal to f of x with degree 3 polynomial from k of x. And our last claim is that the polynomial we have derived as x cubed plus epsilon x squared plus lambda x plus mu is carefree, because otherwise it is supposed that if it can be written as the product of one square factor and one linear factor, then by the equality of y squared equal to f of x, we are able to consider a function y over x minus c. Let me denote it by u. And if you consider this field extension and this equation, first we can see that u square is equal to x minus t, and this shows us the transcendental x is element of ku. And similarly, since we set u as y over x minus c, we can also observe that this transcendental y is also element of k of u, but this gives us indeed our elliptic function field is the rational function field and it has genus 0. But this contradicts to its definition. Then this shows us that this f of x is supposed to be square free.